Davi, and this is my presentation on three coin flip simulation. And in this presentation, I will be comparing and analyzing theoretical and experimental probabilities using spreadsheets. So the purpose of the investigation is to compare and analyze theoretical and experimental probabilities, as I've already said. Uh, and I'm going to simulate this using a spreadsheet to create the three coin flip trials. And there's going to be a set number of trials, like 10, 100, and 1,000 trials, for example, just to show how theoretical and experimental probabilities work, mostly about experimental in the simulation part. I'll be making a histogram to show the random values from the experimental probabilities. I'll show that a little bit more later. And to reach a higher level of explanation and connection here, I'll be connecting these concepts to binomial distribution and expected value. So this is the tree diagram. In the As you can see, we have coin one, coin two, and coin three. These are just the coin flips. I've drawn this diagram myself. And as you can see, for each coin flip, there's always two possible outcomes. So that means that the total number of possible outcomes is 2 to the power 3, which is 8, as you can see. And you can clearly see that each outcome is equally likely, which kind of helps me build the theoretical chart, theoretical probability distribution chart. I actually mean. So in this chart, let x represent the number of heads in three coin flips, right? And then the values of x are 0, 1, 2, and 3. So for 0, the total number of outcomes for 0 is 1. The total number of outcomes for 1 is 3, for 2 is 3, for 3 is 1. You can see it's kind of symmetric. I'm going to talk about that more later too. And yeah, so this table is a general probability distribution because it lists every possible value of the random variable and the probability of each one, which is right here, the probability. And what's funny about this is that you can see that 1 and 2 are actually the most likely to happen, and then 0 and 3 are the least likely. And I figured this out by using this formula. So the number of favorable outcomes and the total number of possible outcomes is equal to the outcomes with x heads. So for example, 0, 1, 2, and 3. So for the outcomes of 0 heads is 1, so 1 over 8. So now let's get into let's get into binomial distribution. Sorry. Let's get into binomial distribution. So the situation I was talking about, theoretical probability distribution, actually follows a binomial distribution because there is a fixed number of trials, which is 3, right? The 3 coin flips, and only 2 outcomes for each trials. So that explains the probability of success of 0.5, which is 1 over 2, or heads or tails, which is kind of binary. And the flips are very independent. Um, so for example, the probability of getting getting two heads, it's p, the probability x equals to 2 equals to 3 choose 2 times 0.5 to the power of 2 times 0.5 to the power of 3 minus 2, which is equal to 3 over 8. And I want you to remember this number and maybe note it somewhere. 0.375, and this is the general equation for binomial distribution. This is a very useful equation, actually. Now let's move on to the spreadsheet simulation. So to simulate this experiment, the spreadsheet generates zeros and ones, which represents the heads or tails, and for each of the 3 coin flips, and then adds the total number to find the number of heads in total, right? So the total is actually to the number of heads, and that using COUNTIF, as you can see right here, we're using rand between to calculate the probability of getting either one or two, or you know, and then we're using sum to calculate the total. So there's two heads right here, and so yeah, and then count if actually counts the frequency of each head. So the frequency of 0 heads, for example, like right here, and right here. So that's three. So let's get into the graph. So I'm not gonna be showing the 100 trials graph and the 1,000 trials graph because they're too long. But I want you to get the general idea from this. Okay, so as you can see in the 10th trial graph, the bars are less balanced. There's not much of a pattern here, right? So there's a more random variation, and yeah, so this is more random. But then in 100 trials, you can see that it actually kind of begins to stabilize here. Um, it starts to take form, right? And then at 1,000 trials, you can see more. It's closer to the theoretical distribution. Um, I just want to show one more trial which I made, and this is actually I'm just gonna be using it to explain what the 10, 100, 1,000 trial means, because this is actually closer to the theoretical probability, and it's even closer than the 1,000 trial. So if you grab your calculator and you go to the number of two heads, it's a frequency of 3759 over 10,000. That's supposed to be 0.3759. That's no coincidence, right? This actually relates right back to the theoretical distribution I was talking about in the binomial distribution. If you remember, we got 0.375 as the value for the probability of two heads, which is about sorry, which is about 37%, and yeah, 37% chance, and that's actually incredibly related to the theoretical distribution chart that I made. I've drawn this line right here just so you understand uh, how the standard like probability distribution should look like. And this is one. So this is the 1/8, 3/8, 3/8, and then 1/8. So that's the probabilities. And now let's get into expected value. So the expected value is actually a weighted average. Um, it's the weighted average outcome actually we expect from a very large number of trials. So as you can see, we start from I, and then we're supposed to end at n, and we're gonna do x times the probability of getting xi, um, and then we're just gonna add this statement right here until we reach xn and probability of xn, right? So this is what I'm trying to say here. So we're starting from x0 to x3 because we're doing three coin flips trials. Or sorry, because of the probabilities we've been talking about here from the theoretical probabilities chart. So you can see you actually get this equation, and if you actually see the value, you get 12 over 8, which is 1.5, and um, I don't want you to uh, I don't want you to understand that you'll get 1.5 heads in a set number of trials or anything like that. This actually means that if we repeated the experiment millions or billions of times, the average number of heads, so the average number of heads per trial would get closer to 1.5, right? And right here, I just want to explain how this actually relates to the theoretical distribution, because as I said, the expected value is just the weighted average. So that means that the expected value of 1.5 is the balance point of the distribution. And even though 1.5 is not exactly a number of heads, it actually is between 1 and 2. So they are like the most probable outcomes, because again 1.5 is the average. So that's why so that's why the graph is actually centered around 1 and 2 heads, and why 0 and 3 heads are actually the least probable to happen. So this actually relates to the symmetry I was talking about, and this is an important feature of the binomial distribution when the probability is 1 over 2. um, yeah, and so for the conclusion and things we learned, I'm just gonna say that the experiment is best modeled by the binomial distribution, because coin flips are independent and the probability of heads stays the same each time. So again, if you do the probability of getting two heads, it's always going to be 0.375 and not 0.3759, right? And as in a hypergeometric distribution is different, because it applies when selections are made without replacement from a fixed group. And I'm just gonna talk about some probably common mistakes that could be made during this experiment. So just for example, one probable mistake is that a small sample like 10 trials might mislead someone and might make them think that's the finished product. But if you actually continue to increase the steps, is actually going to get closer and closer to the theoretical distribution. And yeah, and the formulas can be a little bit tricky. If you get them wrong, you might get the graph wrong, and you might not totally reach or be close to reach the theoretical distribution pattern that we've been talking here. So overall, this entire investigation shows that the number of trials increases, experimental probability approaches the theoretical probability, and that the long run average is actually 1.5. So yeah, so that's everything that I wanted to talk about here. Thank you so much.